Hello everyone, our 11th tutorial class. In this we will be studying plasma technology for renewable energy and environment. We will try to get the insights about the processes, why they happen, what are the underlying physics, how they are beneficial, and why you should adopt them. So, as far as renewable energy is concerned, WTE is a is a very important aspect. What is WTE? It is called waste to energy. Now, in this, actually, what we are doing, we are taking the waste products, and from that, we are trying to either produce, syngas, which is a combination of primarily carbon monoxide and hydrogen, or we are producing, you know, um, pure hydrogen using some membrane technology by which we can separate the hydrogen, or we are converting CO and H2 to methanol using some catalytic converter. Now, one important objective of this processes remains to get rid of the waste. Now, this is a very catchy thing. You have, mountain of waste. If you go to the real dumping yard in municipalities, you will see really they are looking like, hills. Now, what we want actually, we don't want the space occupied by such waste. Just don't want to see that thing. What is the way? The thing is that if you don't want to see something in solid state which physically obstructs our vision, then you can convert them to gaseous state which are not actually visible. Right? How it is I am telling you. Suppose we have, some cellulosic material. So, the C6H12O6 kind of configuration is there. And what are they actually? There are carbon, there is hydrogen, and there is oxygen. But when they have combined together, they made a compound which you can see, which can, which can touch, and which can obstruct your motion, vision, everything. So, what to do? The plasma is having very high temperature. So, the C, H, and O bond, whatever bond is there, suppose it breaks. Then what happens? Carbon is freed, O atom is freed, and H also freed. Now, H will combine with another H, will form hydrogen and go away. So, one you are able to manage. Then, oxygen meets with another oxygen from SO2 and goes away. So, you are able to manage another atom, and they will not be visible because oxygen is not visible, hydrogen is not visible in normal state. Then what happens? Then remain the carbon. Now, carbon as such is solid, but the moment you give it one or two atoms, then what it forms? Either CO, carbon monoxide, if it gets one atom, or it will form CO2 if it gets two atoms. Both of them are gaseous and not visible. So, remember that CO2 is not a black gas, as you may have some feeling. Whatever the black smoke that you find, they are mostly carbon particulates. As such, this CO2 is a colorless, odorless, and rather harmless gas if you just remove the its greenhouse gas property. That is, it is a global warming is caused by such gases. Apart from that, it really doesn't harm you. Rather, the photosynthesis requires this CO2, and without photosynthesis, none of us would exist. So, this CO2 is rather a useful gas, of course. And you know, the Pollution Control Board, if you go to the norms, there is really no clear directive about the limit of CO2, upper limit of CO2 that should be there. But anyway, it is a greenhouse gas that we must admit. So, if global warming is concerned, then this is causing some, concern. So, apart from that, CO2 is not a black smoke. First of all, it is a colorless, it is odorless, and to some extent is harmless gas as well. If you remove this global warming property. So, what we have now done from the C6H12O6? Neither C is visible because it has from CO2, neither H is visible because it has from H2, neither O is visible because it has from O2. So, everything vanished like magic. So, the mountain of waste, or the that was earlier occupying your land. The lands are very precious nowadays, you all know. So, those are not there. So, you can get a clean green environment free from the dirty waste. So, that is the one part of it, that volume reduction. So, whatever the volume was there, if you are able to make all of them gaseous, then nothing is on the ground. So, that is one of the very, very important aspect of this waste to energy technologies. Now, there are three technologies are there. One is called plasma pyrolysis, plasma gasification, and plasma incineration. Now, all these are basically burning of waste. Plasma pyrolysis, what it does actually, because of the very high temperature of the plasma that is used, suppose inert gas, you are discharging argon in some waste, then you are delivering only the heat input. So, what is that causing? This is cracking all the C, H and O bonds. Now, what they are doing? O and H are able to manage to form O2 and H2, and they are going away, but the C which was there, the C is not able to get removed because you are not supplying any external oxygen. So, that is pyrolysis, when you are supplying no additional oxygen. So, there you will see that hazardous wastes are no more hazardous because all bonds are broken, but it will form biochar because carbon is in a very limited quantity. They are combining with the oxygen. If it is there, they are forming CO and H2, but not all carbons are getting enough chance to form CO, so they are staying as a biochar at the bottom. So, complete volume reduction is not possible if you are going for this plasma pyrolysis, where you are supplying zero oxygen from outside. Then comes the plasma gasification, where you are supplying limited amount of oxygen. So, the C that was there, it is now converted almost fully to CO. So, now volume reduction is complete because now all of them has been converted to gaseous product, but the thing is that the gaseous product is mainly now consisting of CO and H2, which forms the fuel gas, is called syngas. If you are able to clean it enough from the carbon particulates, it can work exactly like compressed natural gas, and you can run engines using that thing. And the most significant thing is the volume reduction. You are able to reduce the volume almost 100% here if no other entity is available. Then the plasma incineration comes, where you are burning the waste, but in giving your stoichiometry requirement of oxygen. So, C is forming CO2, but only thing is that you are doing that process at very high temperature, so you are able to break the toxic bonds. So, it is a safe hazardous way of disposal of hazardous waste. Even it can be used for radioactive waste in some cases. So, high volume reduction is there, but no syn gas is produced here, because CO will combine with another oxygen and it will form CO2, and H2 will combine with another oxygen and it will form H2O. So, those have no calorific value as such. So, this is not able to produce syn gas, which was getting produced in case of plasma gasification. So, very clear about the three aspects, three different processes of burning. One is pyrolysis, one is your gasification, and one is incineration, and what is the difference between them, and what are the advantages and disadvantages of them. Now, WTE concept objective is primarily to generate electricity, heat or fuel. Then role of plasma is to convert the non-recyclable waste into clean syngas. So reduce dependency on the fossil fuel, because it is alternate way of generation of the fuel for running engines. Then societal applications, it can do urban waste management like your electronic waste. It can do clean energy production and rural electrification via mini plasma plants it can do. And above all, what it is doing, it is giving you a clean and green environment free from the dirty waste. So that is something very, very important for a society. So this is the WTE concept in summary. Now I go for the technology, that is plasma cutting and welding, where you are using plasma for cutting the high velocity jet, as I have already told in the classes, and the high temperature together. They allows you to cut metals, very thick metals, in a very precise, fast and clean manner. Plasma welding, you all know, nowadays it is very popular. So plasma arc is used over there for high temperature and control. It is ideal for aerospace, automotive and medical device fabrication. It can offer you very high precision and low heat affected zones. So that is important. The heat affected zone surrounding the your location of interest is a concern. Then it can work with conductive materials only. If you are going for your transferring the arc over there. So cold plasma application. The plasma is medicine. Basically, you require a cold plasma because you are going to handle with tissues which are living entities. So cold plasma, non-thermal plasma with electrons at very high temperature, maybe 2 eV, 3 eV, but ions and gas at room temperature. The mechanism is that it generates oxygen and nitrogen species ROS and RNS, induces apoptosis in cancer cells without harming the healthy tissues. The uses are like that: skin, brain or head neck cancers. Clinical trials are going on. So these are, you can truly speaking, these are in research stage and good results are being seen, but they are still not entered in the mainstream plasma medicine, but their potential is understood. Now advantage is that they are minimally invasive and targeted and localized treatment is possible. So these are some application in plasma medicine. Then, as I told you that they are useful for nano composites, and I promised there that there are two kinds of distribution. One is your unimodal and one is bimodal distribution of particle distribution. So how they appear and when they appear, in what systems they appear, that I promised that I will discuss in the tutorial. So here it is. So plasma assisted nanosynthesis is occurring because of top down and bottom up approach. How do you do that thing? See, there are very high temperature ceramic materials. For example, say aluminum oxide, which has a melting point of 2072 degrees centigrade, and yttrium oxide, we call it yttria, it has melting point further higher, it is 2425 degrees centigrade. Now, such material, if you want to go for this top down and bottom up approach followed by actually, so then first thing that you need to melt them. When reaching a high temperature like more than 2025 degrees centigrade, it will just melt. Then you have to evaporate that to make atoms, then atoms will undergo nucleation and then it will form the nanoparticles. So the first step is to top down approach. You give some coarse material particles and evaporate them and form the atoms. Then when they have formed the atoms, then you are going for bottom up approach. So these atoms are now nucleating, colliding together and making bigger and bigger particles, and the coagulation stops at certain temperature. Beyond that, it will collide like billiard balls. They will not join together. So first thing, you have to produce a temperature which is very high, like say more than definitely 2500 degrees centigrade in such cases, and you should have a very high gradient. That is very much required, because you need to stop the coagulation of the atoms. So when their nucleation stops at a certain temperature, that is the final diameter or size of the particle. So they are nucleating, colliding with each other, joining together, and this joining stops at certain temperature, below which you will not get any coagulation of the particles. So that time, whatever the size you achieve, that is the final size. Now the faster you bring down the temperature, finer will be the particle size. This is obvious. The faster the gradient in temperature, the smaller will be the particle size. So gradient in temperature is a very important thing, and depending on the gradient, your particle size will be determined. Now there are two systems. One is arc plasma system and one is radio frequency plasma system. Both of these can generate the nanoparticles. Now in arc, usually you get a bimodal kind of distribution. So you get the peaks at two sides, at lower and one higher. But in case of RF plasma, you usually get only single peak. So the unimodal distribution of the particle size. But in case of arc plasma, you are getting a bimodal distribution. Now where from they appear? So I will go in the next slide. I will explain how do they appear. And before that, what I will do actually, I will tell you where they are getting applied. Why this nanosynthesis is very much important, and where RF plasma is having an advantage over the arc plasma devices. One of the very important application is in the area of transparent ceramics. They are so important that laser gain media like Nd:YAG nowadays for inertial confinement, they are being made using ceramic route, and the ingredients in the ceramic route usually starting from the nanoparticles, and those ceramic nanoparticles can be produced using this plasma in a much better way. Why? This is because this plasma is such a system which can offer you temperature in excess of 10,000 degree Kelvin in a so effortless manner. So that is the key advantage of this plasma system, that it can produce very high temperature effortlessly, like the thermal plasma systems. They are the systems where you can easily get this, and as I told you, arc and RF plasma, they can offer the things, and there the application area involves this transparent ceramics, which involves even the laser gain media like Nd:YAG. So it has a tremendous potential. The other applications are there, that these nanoparticles can be used as drug carriers, catalysts, and biosensors. So these are the other application area which are also important. Now I will explain you how this bimodal and unimodal distribution in the particle size appears. So here are the thing. I have already shown you these figures in our previous slides. Here I show you just to explain you how these two type of distributions appear. Now this is arc plasma. You see the kind of width. This is a very narrow width, and this is the luminous zone. Actual high temperature width is further smaller. So if you go along the axis, you are seeing that more or less similar luminosity appears. So the drop in temperature along the axis is quite less. The gradient in temperature along the axis is low. But if you go on the sidewise, at the center, you will be getting a temperature around 15,000, 16,000 degree Kelvin. But just few millimeters away you are seeing that the temperature is nearly the room temperature. So the gradient in radial direction is extremely high, whereas the gradient in the axial direction is rather low. The high gradient in radial direction causes the particles to have much finer size, because the higher gradient, so the nucleation is stopping much faster, so they are not able to grow enough in size and giving you particles of smaller diameter. Whereas when they are moving along the axis, they are colliding, growing. The dwell time of the particle within the plasma is quite large comparatively. So because of the higher dwell time inside the plasma, they are getting enough time to collide and grow. So they are finally achieving a final diameter which is much higher than the diameters which are observed when they are nucleated along the radial direction. So those particles which are moving along the radial direction, they are offering you a much lower dimension compared to those particles which have moved along the axis. So that is the reason why you are getting two size distribution. One is very narrow, which has originated for the movement of the particles along the radial direction, and one is very large size, which distribution is quite broader. This is expected because most of the particles are moving along the axis and their dwell time is more, so they are growing bigger and they are more in number. So area under this curve gives you the total number of particles. Now in case of RA plasma, what you are seeing here, the diameter is quite large compared to this one, much larger than this one. So the particles which are coming inside, they are getting enough time both in radial direction as well as in axial direction to grow. So as a result, actually they are not producing two sharp peaks at different size locations. So you are getting a single size distribution, because here you see that the temperature in the radial direction as well as in the axial direction, you are feeding the particles on the top, they are getting evaporated over here and then they are nucleating and coming down. So they are getting more or less equal gradient in both radial and axial directions, and that is why they are producing a unimodal distribution. Of course, if you are using a quenching from the radial side, this may result in some different aspects, but usually, typically in your RA plasma system, you are getting a unimodal kind of distribution. So I just give you some idea about this functionalization and targeted drug delivery. Surface functionalization is a very important thing in your fabric industry and as well as in other biofilms, where you want, actually you want to you functionalize the surface. For example, suppose you have a carbon nanotube film and you want to add some nitrogen molecule in that, so that you can make them hydrophilic rather than hydrophobic. So in same thing, if you want to do the surface processing for fabrics, you can make it undergo some cold plasma discharge, and those fabrics will be hydrophilic rather than hydrophobic, and it will extend to the processing a much easier way. Okay. Now targeted drug delivery, functionalized nanoparticles can deliver drugs to disease cells, reducing the side effect. So it will be targeting the disease cells only, not the healthy cells. So the relevance of this functionalization and targeted drug delivery, especially in the cold plasma regime, is cancer therapy, anti-inflammatory treatments, gene therapy, and all these things. So I summarize the items that we have covered. So they are this. In the area of waste management, we are using pyrolysis and gasification. Mostly, outcome is that waste to syngas, sometimes slags we are getting, and hazardous waste and volume induction are the primary are some of the primary objectives. Then in the area of energy production, we are using plasma to generate electricity or fuel from the waste. Then in industry, we are using cutting, welding, so precision machining and metal joining. In case of medicine, we are using mostly cold plasma therapy to kill cancer cells, and for drug delivery as well. In nanotechnology and biomedicine, the plasma process is functionalization and synthesis of, of nanoparticles for drug delivery, and so it is benefit is that it is enabling drug delivery and diagnostics in biomedicine. So with this I finish this tutorial and see you in the next tutorial in the next week.